So let's begin with where our atomic theory comes from. And the first mention of it was in the 5th century BC by these two characters, Leucippus and Democritus. Leucippus is the teacher, Democritus is the student, and these guys were the first to postulate the existence of atoms. But in Greek, atomos, which means unable to be cut or indivisible. And so this is the first instance where someone is postulating that there is a smallest recognizable form of matter. And you can imagine that there were a lot of people who laughed at this idea, including such luminary characters as this guy, whom you might recognize as Aristotle, who did not agree with this. And since Aristotle was one of the founders of modern thinking, you might be not surprised to predict that this idea of atoms was widely disregarded all the way through medieval science thinking and into the Renaissance. But let's skip to the good stuff. This dude rocking this wig is a French scientist, a French chemist by the name of Antoine Lavoisier. As we said, a French chemist whose biggest contributions to the theory were in the late 1770s. And for us, his big contribution is going to be that he was the first to recognize the law of conservation of matter, which says matter cannot be created or destroyed, but changed only in form. This is why we have to balance equations, because in a reaction we have to consider the origin and final resting place of matter, and that's why we have to consider the number of atoms that appear on both sides. There has to be the same one atom of carbon on this side and one atom of carbon on this side. They can't just disappear. So that brings us to, gentlemen, this is Joseph Louis Proust, also from the late 1770s, who was the first to notice that a compound always contains exactly the same proportions of elements by mass. He noticed that this compound, also known as copper 2 carbonate, was always 5.3 parts copper to 4 parts of oxygen to 1 part carbon. That looks like this. And this has two meanings for us. Whether the copper 2 carbonate was synthesized in the laboratory or natural, these ratios are always a constant. It doesn't matter how much mass we have, they will always be in this constant ratio of masses. So from Proust, we get the law of definite proportions. From this dude, whose name is Dalton, we get the law of multiple proportions. This made its appearance in 1844, and here's what that says. The same two elements combine to form more than one compound. When we mean more than one compound, we mean a compound involving elements X and Y, and they could form compounds with different ratios, these elements. It says the mass of one element in the first compound to its mass in the second compound, as it combines with the same mass of the other element, can always be expressed as ratios of small whole numbers. Let's take an example. We have two compounds here, carbon monoxide and carbon dioxide. And what it says is that when we combine carbon, 3 grams of carbon, With oxygen and carbon monoxide, it requires 4 grams, and that's cool. And that the ratio of the oxygen that combines with carbon has got to be a whole number when compared to the mass of oxygen that combines with carbon in the second. So for example, 3 grams of carbon in the first, right here. And the ratio of oxygen to carbon is 4:3. In the second example, the ratio of oxygen to carbon is 8:3. If we compare that 8 grams of oxygen combining with 3 grams of carbon to the 4 grams of oxygen combining with 3 grams of carbon, we get a whole number ratio of 2:1. Now, if that isn't ringing a bell, or if that isn't clicking yet, think of it like this. First evidence that matter forms in discrete whole numbers. In other words, the first proof that atoms exist. Well, this is 1844 we're talking about, so it took us a while to get here, but once we did, we took off. Let's take a few more points from Dalton. From Dalton, we get 4 crucial points. 1. Each element is made up of atoms. 2. Atoms of a given element are identical. 3. Chemical compounds form when atoms of different elements combine. A given compound always has the same relative number and types of atoms. And 4. Reactions involve the reorganization of atoms, but the atoms themselves remain unchanged. Here's an interesting little aside into finding out masses of different elements. Dalton knew is that atoms of hydrogen and atoms of oxygen were necessary to make water. And he also knew that whenever you combined oxygen and hydrogen to make water, the mass of oxygen involved was always 8 times that of the mass of the hydrogen involved. And so he just arbitrarily assigned a mass of 1 to the hydrogen atom and a mass of 8 to the oxygen atom. They did not know anything about atomic masses at this time. They just knew that oxygen was bigger. And then run into this guy, Lusac, and his law of combining volumes, which looks like this. Here's what we have. When hydrogen gas combines with oxygen gas, you always have twice as much volume of hydrogen as oxygen. And when they're done combining, you get twice as much volume of water vapor as you did of original oxygen, and the exact same amount of water vapor as the original hydrogen. And what this tells us is that no matter how much hydrogen we have and oxygen we have, they're always combining in a volume of 2:1. And so if the oxygen has a mass of 8 and the hydrogen has a mass of 1, relatively speaking, and they're combining in volumes of 2:1, that must mean that the oxygen has a mass of 16 relative to hydrogen's 2. This is the first evidence we see of atomic mass. So Dalton proved the existence of the atom. But what does an atom look like? Well, J.J. Thomson in 1903, that's this guy, was the first to show that atoms had both negative and positive charge. But he didn't know too much about where these charges were located, so his first model of the structure of an atom looked like this. What we call the plum pudding model, because Thomson knew that they were both positive and negative charge. from his experiments with a cathode ray tube. We're not going to get into how he got this theory, but he knew that the negative charge was separable from the positive charge, but that the atom overall was electrically neutral. So it had to have both positive and negative charge, but he didn't know where they were. So he just assumed that it was a spherical cloud, this positive charge goo, and that the electrons were just randomly interspersed throughout this positive cloud at random. In 1911, we have Ernest Rutherford. He looks like this. And he was the first to show that the positive charge is concentrated in the center. And how he did this was pretty cool, so I'll show you this. He did it by shooting a stream of positive charge at atoms. And his theory was that if the structure of the atom conformed to the Thomson model, that the stream of positive charge would just blast right through it. But instead, what he noticed was that every once in a while, if he shot this stream too close to the center, the positive charge would be repelled almost, in some cases, straight back at the source of the emissions. So it led to him to believe that the source of the positive charge in an atom was located in the center, and that's where we get this model of atomic structure, where all of the positive charge is concentrated in something called the nucleus, and that the electrons orbit at extremely high speed. This model is pretty wrong, but it holds for what we're looking at now. A couple other people that we want to mention, because we'll get to the Bohr model of the atom soon enough, but let's mention a couple other people. So we got this guy, Henri Becquerel, in 1896, and he looked like this. Got a rockin' beard and stash combo, and he was first to demonstrate the existence of radioactivity in uranium. And obviously we know that Madame Curie went on to achieve great to make great inroads and progress on the study of radioactivity. And lastly, we have Robert Millikan in 1909. He looks like this, and he was the first to determine the mass of an electron, 9.1 times 10 to the negative 31 kilograms, but the upshot of his experiment was that he was also able to calculate at 1.6 times 10 to the negative 19th coulombs. We'll play around with that more in chapter 18. So that brings us to this. We know the mass of a proton is 1.673 times 10 to the negative 27 kilograms. We know the mass, let me make that smaller, of a neutron is 1.675 times 10 to the negative 27 kilograms. And we know the mass of an electron is 9.1 times 10 to the negative 31st kilograms. We know that atomic charge, for example, the charge on a proton with the charge of an electron is 1.6 times 10 to the negative 19th coulombs. They are equivalent. And lastly, the diameter of the average nucleus is 1 times 10 to the negative 13 centimeters, and that the diameter of the simplest atom on average is 1 times 10 to the negative 8 centimeters. Quite a lot to absorb. All right, I'll see you on the next one.